Let's determine the effect of temperature on volume. To do this, we are going to use a setup similar to that we used to determine the effect of temperature on pressure. In this case, however, we will attach a syringe to the fixed volume flask with the valve now open between the syringe and the flask. In this experiment, the temperature will be changed and the volume in the syringe will be adjusted to maintain a constant pressure. When we record the volume for plotting purposes, we will add the volume of the syringe to the volume of the Erlenmeyer flask. To determine the actual volume of the flask, it was filled with water and stopper pushed down to exclude its volume. For this particular flask and stopper combination, the volume turned out to be 143 milliliters. Let's set up the plotting and data collection for this experiment on Logger Pro. I will change the independent axis for the top plot to temperature, and now we'll go to Experiment, then Data Collection, and switch the mode to Events with Entry, with the entry changed to volume with units of ml. We need to change the dependent axis to volume now so that we have volume versus temperature. Also, let's just show the one top plot by pulling it over the bottom plot. We can set up the axis limits to fit within the temperature ranges and volumes we might expect. We can adjust later as necessary. Since the flask volume is 143 milliliters and the attached syringe is 60 milliliters, the maximum volume that we could run in this experiment would be a little over 200 milliliters, and the minimum would be about 140 milliliters. An ice alcohol bath will be used to get the temperature below zero, and nearly boiling water will be used for the high temperature. The limits for the x-axis will be minus 40 to 100. Now it is time to collect data at our various temperatures. We are set for the initial conditions with the given pressure and temperature. Since the syringe is set at 30 milliliters, the total volume, therefore, is 143 plus 30, or 173 milliliters. As you can see, the pressure is fluctuating a little bit. The challenge will be to adjust the pressure back to approximately 0.975 atmospheres after the temperature has been changed by adjusting the volume of the attached syringe. Now for the first temperature change by adding nearly boiling water. The temperature shoots up as well as the pressure. While I am continually moving the flask to get even temperature distribution, I'm trying to expand the syringe volume so the pressure returns back to the 0.975 atmospheres. At the point I think I have it, I hit keep and enter the new volume of 143 plus 60. Now for a warm water temperature. I dump out some of the hot water, add some tap water to get somewhere between hot and room temperature. As before, I mix and adjust the syringe volume to re-achieve the original pressure. The syringe volume for this time is 50 milliliters. Therefore, I keep the value of 143 plus 50 for this data point. Next up, ice water. After throwing in some ice, adding some cold water, and then after cooling down, adjusting the volume to the original pressure again, the volume was now 15 milliliters, which makes the total volume to be 158 milliliters. Finally, an ice alcohol mixture was added. The temperature got too cold such that all the air was pushed out of the syringe and the pressure was below the target of 0.975 atmospheres. So adding back and forth some room temperature water was necessary to get some air in the syringe with that target pressure. Finally, it was 5 milliliters for a total of 148 milliliters. The data lines up fairly well. Maybe the 50 degree pressure is too high, or maybe the 83 degree one has a pressure that is too low. Let's look at the line fit. The correlation is pretty good. Perfect would be 1.000. Now, what is the temperature predicted if the volume would go to zero? Let's adjust the volume y-axis lower limit to 0. Then try some possible lower limit of the temperature to see when the lower limit exceeds 0 volume. And in this case, we'll try negative 300. We can move the cursor to find the approximate 0 point. It looks to be about negative 268 degrees C. Alternatively, we can rearrange the calculated volume equals mx plus b and solve for x when the volume is 0. Here is the equation with the values plugged in. then rearrange with x calculating to be negative 269 degrees C. This is very close to the accepted absolute zero value of negative 273 degrees C.